Space is silent, cold, unfathomably vast, and yet within its darkness hides a chaos so mysterious it defies everything we think we know. We send telescopes across galaxies, launch probes beyond planets, and name equations after the things we still don't understand. But the deeper we look into the universe, the more it looks back with paradox. Time folds, light bends, reality glitches, and nothing, not even nothingness, behaves the way it's supposed to. This isn't just science, it's a confrontation with the unknown. These mysteries are not puzzles to solve. They are mirrors that reflect our deepest ignorance and our endless curiosity. And in their silence, they ask us questions no one knows how to answer. So lie back, close your eyes, let your mind drift into the stars, because tonight we'll explore 20 of the most unsettling, fascinating, and unsolved paradoxes of space. Imagine looking up at the night sky and seeing a star twinkling faintly in the distance. Its light reaches your eyes, whispering across the cosmos, a journey that may have taken millions or even billions of years. You smile, perhaps unaware that what you're seeing might no longer exist. This is the unsettling beginning of a deeper mystery, one that physicists, astronomers, and philosophers alike have quietly circled for decades. The paradox of light arriving before its source challenges not only our understanding of cosmic distances, but the very nature of time, causality, and observation itself. We know that light travels at a finite speed. When you observe a galaxy a billion light years away, you're not seeing it as it is, but as it was a billion years ago. But here's where things begin to bend. What if the star or object you're seeing never actually existed in your timeline? What if the light that reaches you came from a source that has no local reality at all? In rare but increasingly observed cases, scientists have detected phenomena, gamma-ray bursts, gravitational lensing effects, quantum fluctuations, where light seems to appear from nowhere. In some interpretations, the light we detect doesn't have a clear, linear origin. It suggests a backward ripple in space-time, as if the light took a shortcut through dimensions we don't yet understand. In essence, the effect arrives before the cause. Even more haunting is the role of observation in this paradox. Quantum physics already tells us that particles can exist in multiple states until observed. Could light behave similarly on a cosmic scale? Could the act of seeing be what retroactively summons its source into being? There's a chilling possibility here, that the cosmos doesn't behave like a giant machine, but like a dream, manifesting retroactively based on consciousness and observation. What if the light wasn't waiting to be seen, but was only made real because it was seen? This idea grows even stranger when you consider gravitational lensing. Massive galaxies can bend light from more distant sources around them, creating illusions, images of stars duplicated, warped, or appearing in places they shouldn't be. Some of the stars we see in these effects are Einstein crosses, where the same object appears 4 times in the sky. But what if the original source is long gone, burnt out, swallowed by a black hole never to shine again? What then is the light we're seeing? Is it a ghost, a cosmic echo, or something that only exists because of how the fabric of space and time chose to reveal it? Now imagine this on a human level. You look at a star, you marvel, you feel awe, but the truth is, you're engaging with something that may never have coexisted with you in time. Something that should be long dead, something that shouldn't, in any meaningful way, still be here. And yet, it is. That light, that ancient glimmer, has outlived its creator. It outpaces decay. It defies distance. And in its journey across time, it reaches you. A fragile, wondering, mind suspended on a pale blue dot. This paradox isn't just about physics, it's about presence. About how even in a cold and indifferent universe, something as small as a photon of light can carry meaning across impossible gulfs of time. That what no longer exists can still make you feel something. That echoes are sometimes louder than voices, and perhaps, in some strange way, you are the destination the light was always meant to find. There's a type of silence in space that isn't empty. It's expectant. It waits. It listens. And sometimes it surprises us with something that breaks all the rules we thought the universe obeyed. One such surprise came in the form of a star. A glowing, burning sun so ancient, so pure, so impossible, that its very existence whispered a question into the minds of every scientist who observed it. How are you even here? This is the paradox of the star that shouldn't exist. In 2014, astronomers discovered a star known as SMSS J031336670839-3. A mouthful, yes, but what it represents is far more profound than its name. This star is over 13.6 billion years old, meaning it formed just after the Big Bang itself. But here's the mystery. Based on everything we understand about stellar formation, this star shouldn't be possible. You see, stars are born from clouds, of gas and dust. The very first stars, called population 3 stars, were made from only hydrogen and helium, the two elements created during the Big Bang. These stars were massive, short-lived, and unstable. They exploded as supernovae and seeded the universe with heavier elements like carbon, oxygen, and iron. Elements essential for forming second-generation stars, like our Sun. But this star, it has almost no heavy elements at all. It's one of the purest stars ever found, just hydrogen and helium with a trace of carbon. That means it somehow formed before the universe had enough metals to support long-lasting stellar birth. It's as if this star stepped out of an ancient age of fire, skipped death, and quietly kept burning, long past its expected expiration. It shouldn't exist, not according to the rules, and yet, it's here. So, how do we explain it? Some scientists believe it might be a freak survivor of the first stars. Maybe, just maybe, it formed differently than expected. But the equations don't line up. The math resists it. Others whisper more unsettling theories. Perhaps we don't understand stellar evolution as well as we think. Perhaps the early universe had different conditions, or forces, or laws we've never accounted for. Or perhaps we've missed something bigger. What if the universe isn't unfolding in one clean linear path? What if there are anomalies, glitches, echoes, remnants of previous cycles of existence that didn't fully dissolve? This star may be more than just an old light. It may be a leftover from a cosmic iteration before this one. Think of it like a crack in the fabric of time, a single ancient survivor drifting through the modern universe, untouched, unchanged, bearing witness to an era no longer supposed to exist. Even more disturbing, if one star slipped through, how many others are there? Could there be entire structures, older than the universe itself, hiding behind black holes or veiled in invisible matter? And if time has cracks, if reality has seams, what else might have fallen through? This star, this ancient flame, is a cosmic paradox that asks not only what came before, but how much we've forgotten. It challenges the idea that we are the apex of cosmic understanding. It reminds us that even with all our telescopes, equations, and models, we are still standing on the edge of a mystery so vast, it hides impossibilities in plain sight. A star that shouldn't exist still burns, and in its impossible light, it quietly watches us back. Galaxies are the grand tapestries of the cosmos, swirling spirals of stars, gas, dust, and dark matter, woven together across billions of light years. We study them to understand cosmic evolution, gravity, and the mysterious expansion of space. But every so often, we encounter a galaxy that doesn't just defy classification, it defies time itself. This is the paradox of the galaxy without time, a cosmic structure that appears suspended outside the typical progression of age and development, a galaxy that seems to have missed time's memo entirely. In 2022, scientists using the James Webb Space Telescope discovered several massive, fully formed galaxies that existed a mere 500 million years after the Big Bang. By all current models, this shouldn't be possible. At that point in the universe's infancy, galaxies were supposed to be small, chaotic, and slowly coalescing. Not fully developed, structured systems teeming with stars. And yet, there they were. Bright, organized, mature. These galaxies didn't look like cosmic infants. They looked like they had aged billions of years, but somehow they had done so in a fraction of that time. The paradox deepens when we realize that time, as we experience it, is deeply tied to entropy, the gradual increase of disorder in a system. Things are born, they grow, they decay. That's the arrow of time. But these galaxies seem to have skipped the middle, as if they were born old, as if they emerged not from chaos, but from order. So how did they form? Did time flow differently in that region of space? Did some unknown mechanism accelerate their development? Or are we witnessing a cosmic illusion, something that looks familiar but was never truly part of the timeline we understand? There are theories, of course. Some scientists suggest that dark matter, the invisible scaffolding of the universe, might clump faster in certain regions, creating gravitational wells that accelerate galaxy formation. Others hypothesize that we're observing the after effects of a previous universe, bleeding into this one through phenomena we don't yet understand. But there's another, more unsettling possibility. What if our concept of time isn't universal? What if different parts of the universe experience time differently? Not metaphorically, but physically. We already know that gravity can warp time. Near a black hole, time slows dramatically. Could similar warping occur across vast cosmic scales? Could some galaxies exist in pockets of space-time where the rules are slightly bent? If so, then these galaxies might not just be anomalies. They might be windows into the flexibility of time itself. Even the concept of cosmic age begins to dissolve under this light. If time is relative on a grand scale, then the age of a galaxy isn't fixed. It depends on how and from where you're observing it. And if that's true, then time, as we know it, is more of a local phenomenon than a cosmic truth. This idea reshapes everything. It means the universe doesn't tick forward like a cosmic clock. It pulses, it stretches, it folds, and in those folds, paradoxes are born. The galaxy. Without time is more than a scientific puzzle. It's a message from the edge of reality, reminding us that our most basic assumptions can be shattered with a single image from a telescope. That time, which governs our every breath, might not be the ruler of all things after all. And maybe, just maybe, there are entire regions of the universe where time was never invited in the first place. Planets orbit stars. It's one of the simplest, most foundational truths in astronomy. Stars are the gravitational anchors, cosmic fires around which planets dance in faithful ellipses. Our entire understanding of planetary systems depends on this balance: mass, motion, and mutual pull. But what if that foundation cracks? What if there are planets, that orbit nothing at all. Welcome to the paradox of the planet that orbits nothing. A cosmic body adrift in the dark, untethered, unbound, and quietly defiant of the laws we thought governed its existence. These are known as rogue planets, and they are not a theory. They're real. In fact, astronomers believe there may be billions of them in our galaxy alone. Cold, dark worlds drifting between stars, isolated in the vastness of interstellar space. Some are massive, like Jupiter. Some may even be Earth-sized. But all share one haunting trait: they orbit no star. They drift alone. But how did they get there? The prevailing explanation is ejection. During the chaotic early days of a planetary system, gravitational turbulence can fling a planet out of its home orbit, banishing it from the star that birthed it. The planet becomes a cosmic orphan, a lone traveler. It makes sense until you start noticing that some of these rogue planets are too stable, too common, and in some cases seem to have formed without ever having a star at all. That's where the paradox deepens. Planets are supposed to form from the protoplanetary disks that surround young stars. No star, no disk, no disk, no planet. So how are these planets even forming? And why are there so many? Could they be forming directly from collapsing clouds of gas, like stars, but simply never reach the mass required for nuclear fusion? If that's the case, where do we draw the line between a failed star and a planet? And more curiously, if planets can form this way, outside of any solar system, what else might they form with? Moons, atmospheres, life. We always assumed life required a star, but rogue planets may still retain internal heat, especially large gas giants. Some may even have subsurface oceans, kept warm by radioactive decay or tidal forces from their own moons. Imagine a hidden ocean beneath miles of ice on a planet lost in absolute darkness, completely invisible to us, and possibly harboring life we'll never find. And then there's the other possibility, the more unsettling one. What if these planets aren't naturally rogue? What if some were made to be that way? Artificial displacement, interstellar engineering, remnants of civilizations that once had the technology to move planets. Ideas that sound like science fiction until you remember how little we truly know about the cosmos. The paradox lies in this simple, disarming question. Why do we assume everything must be anchored? Maybe the idea that planets must orbit stars is just another anthropocentric assumption, born from our one lonely example. Perhaps in the grand blueprint of the universe, isolation is not an error, but a pattern, a natural outcome of cosmic entropy, a reminder that not all worlds are meant to be seen. Not all stories are told in light. These wandering planets challenge our categories, our expectations, and our definitions of what it means to belong. They are not tethered, and yet they endure. Not part of a system, and yet whole. Not orbiting, but still moving, endlessly, through a universe that neither welcomes nor resists them. And perhaps, in some strange way, we are not so different. In the silence of space, we listen. Giant radio telescopes scan the heavens day and night, collecting whispers from stars, static from cosmic radiation, and the faint breath of distant galaxies. Most of what we hear is noise, predictable, explainable, mathematical, but sometimes something unusual arrives. A sound, a signal, a spike in the silence that shouldn't be there. This is the paradox of the signal from the end of time, a transmission that, if interpreted literally, comes from somewhere and somewhen it has no business existing. In 1977, a radio telescope in Ohio picked up a burst of energy from deep space. It lasted 72 seconds. It was narrowband. It matched no known natural phenomenon. The technician who spotted it in the data circled it and wrote one word in red pen. Wow. The wow signal, as it came to be known, has never been explained. It has never repeated. It simply was. But it's not just the wow signal that haunts the scientific community. It's the idea that signals could be arriving not only from other regions of space, but from different points in time. Some physicists, especially those working in quantum cosmology and the holographic universe theory, have speculated that time and information are not as separate as we think, that under the right conditions, data, like a signal, might not be bound to linear progression. In this view, the future already exists. The past is not gone. Everything is part of a vast, layered now. And in this layered reality, strange echoes might leak from one timeline into another. Not time travel in the sci-fi sense, but time leakage, where data escapes its era and arrives unnaturally early or late. The idea is almost too strange to accept, but quantum physics has already proven that entangled particles can influence one another across vast distances instantly, violating what we know about space and time. Some theories even suggest retrocausality, effects influencing causes. So if particles can communicate backward through quantum entanglement, could larger patterns like data or signals do the same? Could the wow signal, or something like it, be a message from a future civilization sent across a medium we don't yet understand? Or even more chilling, could it be a final echo? A death cry? Not a message sent with intention, but a remnant of something collapsing at the very edge of time. Physicist James Gates once suggested that when we analyze string theory equations, we find patterns resembling computer code, embedded error correction, as if the universe itself runs on some form of information structure. If this is true, then perhaps some signals aren't meant to communicate. They're bugs, or glitches, or system messages leaking through cosmic firewalls. Imagine this. A signal arrives from a region of space where stars no longer burn, where entropy has won, where time has stretched so thin it can no longer hold itself together. A message escapes, that void, not to warn, not to teach, but simply because information cannot be destroyed. And in its escape, it reaches us. Now, in the middle of our timeline, in the middle of our ignorance, and we stare at the data, confused, recording it, debating it, never understanding that what we're hearing might be our own future crying backward. This paradox is not about proof, it's about possibility, because if time can leak, if signals can bleed across the veil of now, then reality is not what it seems. It never was. And every time we listen to space, every time we tune our machines to the void, we are not just listening to what's out there. We might be listening to what's already happened, or to what hasn't happened yet. Darkness. In the cosmos, it means absence. The absence of stars, of light, of heat. A black void so absolute, it seems to swallow even imagination. But what if that darkness isn't empty? What if it's not silent? What if, instead of absorbing energy, it radiates it? This is the paradox of the darkness that emits energy, the mind-bending mystery that something completely black can shine. To understand this paradox, we need to travel to the edge of physics, to the mouth of the most terrifying objects in the universe: black holes. Black holes are supposed to be cosmic prisons. Nothing escapes them. Not light, not matter, not even information. They're the ultimate endpoints, where time warps and space collapses. You fall in, and you never come out. But in 1974, physicist Stephen Hawking proposed something that shook this understanding to its core. He theorized that black holes aren't completely black. Instead, they slowly emit energy, a phenomenon now known as Hawking radiation. This energy isn't coming from inside the black hole, but from the quantum foam just outside its event horizon. In this strange zone, particles constantly pop in and out of existence. Occasionally, a pair appears near the black hole's edge. One particle falls in, the other escapes. The escaping particle becomes real energy, drifting into the universe as radiation. Over billions of years, this trickle of energy adds up, and eventually, the black hole evaporates completely. In other words, the darkest thing in the universe, the ultimate devourer, glows. It doesn't shine brightly. It doesn't light up the sky, but it emits. And in doing so, it slowly dies. This is the heart of the paradox. A black hole is defined by its invisibility, its absolute silence. But through quantum effects, it has a lifespan. It radiates. It interacts. It is not an eternal grave. It's a ticking clock. And here's where things grow more disturbing. If black holes emit Hawking radiation, that means they lose mass over time. They shrink. They wither. And with them, so too goes every particle, every memory, every encoded secret that ever fell inside. This leads to the information paradox, one of the greatest unsolved problems in physics. Quantum theory says information can't be destroyed, ever. But if a black hole evaporates completely, where does the information go? Does it get smeared across the event horizon, encoded in the radiation? Is it lost forever? If it's truly gone, then something in our understanding of the universe is fundamentally broken. Either quantum mechanics is wrong, or our understanding of space, time, and gravity is. And we're not talking about obscure theory. We're talking about the rules that govern everything. The idea that a black hole can glow opens a crack in our view of the cosmos. It shows us that even the things we think are dead, cold, final, complete, are still active in ways we barely comprehend. We've always feared black holes as endings, but they may be transformations. Their darkness might not be a void, but a veil, one that hides a process stranger than we've ever imagined. A darkness that emits energy is a contradiction in our senses. It tells us that light and dark aren't opposites. They are entangled, that what disappears still leaves echoes. That silence, even cosmic silence, has a voice. And if that's true for black holes, what else might glow in the dark? What other cosmic absences might only appear empty while quietly unraveling reality beneath their surface? This paradox isn't just about astrophysics. It's about how we define endings, and whether anything at all, can truly disappear. Across the vast gulf of space, stars flicker and fade. Planets orbit in silence, and entire galaxies vanish behind time. But what if, beneath that silence, there are echoes? Not the kind that bounce off walls, but something stranger. Something quantum. Something that suggests that every decision, every observation, every reality might be connected, even across impossible distances. This is the paradox of the quantum echo of distant worlds, a haunting possibility that faraway planets, perhaps even those we cannot see, still somehow influence us, and that we, unknowingly, might influence them. At the heart of this paradox is one of the most baffling phenomena in quantum physics, entanglement. When two particles become entangled, their states become linked, no matter how far apart they are. Change one, and the other responds, instantly, even if they're light years away. Einstein called it spooky action at a distance. But today, we know it's real. Now imagine that on a cosmic scale. What if some particles on Earth are still entangled with particles that originated from other corners of the universe? Perhaps from ancient stardust? Or from collisions that happened before Earth even formed? It's possible, in theory, that quantum connections span the galaxy, binding systems in ways we've never been able to detect. That would mean that what happens here might cause ripples there, and what happens on a distant exoplanet light years away could, somehow, still be felt here. It's not just a poetic idea. Some physicists speculate that quantum entanglement could serve as a foundation for understanding how information travels in the universe. If space-time itself is woven through quantum relationships, then there may be echoes, not just of sound or radiation, but of reality itself, stretching between distant worlds. Here's where things become deeply unsettling. Let's say there's a distant planet, uninhabited, unknown. We've never seen it. But due to a long-forgotten cosmic event, maybe a supernova or a collapsing star, a few atoms from our solar system became entangled with atoms from that world. Now imagine you interact with one of those atoms, measuring it, observing it, altering it in some subtle quantum way. Does something change on that planet? Not obviously, not visually. But beneath the surface, on the level of pure potential, has something shifted? And if that's possible, how many such entangled echoes exist between Earth and the stars? Maybe there are threads, invisible filaments of shared quantum history, connecting us to every planet ever touched by the same stardust. Maybe entanglement is not just a strange side effect of physics, but the nervous system of the universe, whispering between realities in a language we haven't yet learned to hear. And here's another eerie possibility. What if entanglement isn't limited to particles? What if consciousness itself plays a role? Some fringe theories suggest that observation creates reality, that to perceive something is to bring it into being. If so, and if distant worlds are entangled with us, then the mere act of looking or thinking might send ripples through space-time. It may sound like science fiction, but in quantum physics, observation already alters the outcome of experiments. The observer and the observed are not separate, and the farther we go into the quantum world, the more we find that everything is entangled. Not just particles, but possibilities. So what if distant planets remember us? Not in memory, but in entanglement. What if they echo with our choices, our attention, our very presence? And what if we carry their silence in us too? In this view, the universe isn't just a backdrop for life. It's an interconnected web, where time, distance, and matter are illusions of scale, where everything touches everything else, and somewhere in that invisible web, you are already touching stars no telescope will ever find. When you think of a void, what comes to mind? Silence, emptiness, a perfect absence of light, of matter, of meaning. Space, after all, is made mostly of nothing. Vast regions between galaxies stretch out in seemingly infinite darkness, where no stars shine and no signals arrive. These are the cosmic voids, regions so barren, so still, that they feel like the quiet places where the universe forgot to finish its story. But what if those voids aren't empty at all? This is the paradox of the void that isn't empty. The strange and disorienting discovery that what we've always considered nothing might actually be teeming with invisible energy and unknown forces. Let's start with the vacuum of space. In classical physics, a vacuum is the absence of particles. No atoms, no radiation, no pressure. But quantum physics tells a different story. According to quantum field theory, even a perfect vacuum is not truly empty. It is boiling with potential. Particles and antiparticles constantly flicker in and out of existence. This background activity is known as vacuum energy, and it's not hypothetical, it's measurable. In fact, this vacuum energy may be responsible for something far greater, the expansion of the universe itself. Scientists once believed the universe's expansion would gradually slow down due to gravity, but in 1998, two teams of astronomers discovered something shocking. The expansion of the universe is accelerating. The cause? Something we now call dark energy. Dark energy makes up about 68% of the total energy in the universe, and yet we don't know what it is. One possibility? It's the vacuum energy, the energy of the void. If that's true, then the vast empty spaces between galaxies aren't empty at all. They are alive with a force that drives galaxies apart, reshapes space-time, and stretches the very fabric of reality. This flips everything we thought we knew. Nothingness, it turns out, may be more powerful than anything. But it doesn't end there. Some voids in space, like the Botez void, an enormous region 330 million light-years across, are not just empty of stars. They're so massive, so unexplainably barren, that scientists struggle to explain their existence. They challenge our models of cosmic structure. They seem to resist formation, almost as if something prevented matter from accumulating there in the first place. What if these voids aren't the absence of matter, but the presence of something else? Some theories suggest that voids could be where the multiverse interacts with our own, regions where another universe, invisible to us, suppresses the formation of galaxies. Others propose that these voids are topological features in space-time itself, like dents or bubbles in the underlying quantum field. And then there's the existential layer. If something can look empty and still be full of energy, force, and motion, what else might appear empty but isn't? Maybe consciousness behaves like a void. Still, silent. But beneath the surface, filled with flickers of thought, waves of feeling, entire galaxies of memory. We think of ourselves as individuals in a vast, indifferent cosmos. But perhaps, like the void, we are more than we appear. Perhaps our most empty moments are where the deepest forces stir. This paradox dismantles the idea that nothing is nothing. It suggests that silence has structure, that absence has depth, that behind every place we think is barren, there may lie the engine of creation itself. The void isn't lifeless, it's the womb of the universe, and from it, everything emerges. Not despite the emptiness, but because of it. So the next time you look up at a dark patch of sky, don't assume you're seeing nothing. You may be staring directly into the most active place in existence. Gravity is the quiet artist of the universe. It paints the orbits of planets, shapes the arms of galaxies, and keeps the fabric of space from flying apart. We cannot see it, but we feel its presence everywhere. It is predictable, constant, and familiar. But what happens when gravity pulls and there's nothing there? This is the paradox of the gravity that pulls from nowhere. The unsettling realization that something invisible, something we've never seen or touched, is exerting immense gravitational force across the cosmos. The story begins in the 1930s. When astronomer Fritz Zwicky was studying the Coma Cluster, a massive group of galaxies, he noticed something strange. The galaxies were moving far too fast to be held together by the visible matter alone. By all logic, they should have been flung outward into space. But they weren't. Something unseen, something with mass, was keeping them in orbit. That something was later named dark matter. Fast forward to today, and dark matter is one of the biggest mysteries in science. It's estimated to make up about 27% of the universe, yet we've never detected it directly. It doesn't emit light. It doesn't absorb it. It doesn't interact with electromagnetic forces the way normal matter does. And yet, it has gravity. It pulls on stars. It bends light. It shapes the large-scale structure of the universe. In fact, if dark matter didn't exist, galaxies themselves wouldn't hold together. They would unravel, disperse, disappear. So what exactly is this invisible force holding the universe together? We don't know. There are theories, of course. Some scientists believe dark matter is made of exotic particles like WIMPs, weakly interacting massive particles, or axions, particles that rarely interact with regular matter, making them nearly impossible to detect. Others propose that dark matter might be primordial black holes, tiny remnants from the early universe scattered like seeds through space. And then there are the more radical ideas. What if there is no dark matter at all? What if our understanding of gravity is simply incomplete? Some alternative theories, like modified Newtonian dynamics, MOIND, suggest that gravity behaves differently on cosmic scales, that maybe it weakens more slowly with distance than we thought. In this view, the missing mass isn't missing. It's just that our equations are wrong. But regardless of the theory, the paradox remains. Something is pulling, and we don't know what it is. We're left with this haunting contradiction. Gravity, the most familiar of all forces, is acting in ways we can't explain. It pulls from regions where nothing is visible. It shapes the cosmos from behind a curtain we can't lift. This should disturb us. And it does. Because if 27% of the universe is made of a substance we can't detect, what else might be out there? What if dark matter is only the beginning, a shadow cast by something even deeper? Some physicists suggest that dark matter might interact not with our universe, but with another. That it could be matter from a parallel dimension, whose gravity leaks into ours. If so, we may be surrounded by an invisible universe pressing against us in ways we barely perceive. It makes you wonder, how much of reality is shaped by what we don't see? How much of our lives, our choices, our perceptions are tugged by forces that never reveal their face? This paradox doesn't just reshape astrophysics. It whispers something deeper, that the most powerful forces are often the ones we never notice. That reality is held together not by what is seen, but by what refuses to be seen. Gravity pulls from nowhere, and in that pull, we are bound to mystery, to motion, and to a universe that is not yet finished revealing itself. You move through life like a ripple in time. You speak, breathe, think, and then move on. The moments pass, the memories fade, and the universe seems indifferent to it all. And yet, what if it isn't? What if somehow, somewhere in the structure of reality, you are never forgotten? This is the paradox of the universe that remembers you, the haunting idea that no thought, no choice, no breath is ever truly erased from existence. We're taught that time moves in one direction, forward, that what's done is done, and the past becomes unreachable. But in physics, this isn't entirely true. According to the laws of quantum mechanics, information cannot be destroyed. Every interaction, every particle collision, every event in the universe encodes information about what happened, even if it's scattered beyond recognition. This leads us into the strange world of the quantum information paradox, especially when paired with black holes. Stephen Hawking once proposed that information is lost when it falls into a black hole. But this contradicts the principles of quantum physics. The conflict sparked decades of debate until a newer idea emerged. Maybe the information isn't lost. Maybe it's stored on the event horizon, encoded in some unfathomable language of light and spin, a kind of cosmic memory field. Now stretch this concept beyond black holes. What if every part of the universe has the ability to store traces of what has passed? Not in a conscious way, but in the structure of reality itself. Maybe space, like a great cosmic mirror, keeps an impression of everything it's witnessed. A photon that bounces off your face may travel across the universe forever. It carries a record of your existence, not in meaning, but in mathematics. The pattern of your movement, the reflection of your eyes, the temperature of your skin, all stored in light, scattered endlessly. You are not as forgettable as you think. And then there's the growing field of holographic principle, a radical theory that suggests all the information contained within a volume of space can be described by data encoded on its boundary. This means the universe might be a projection, a 3D experience emerging from 2D information written on the edge of reality. If this is true, then everything you are, your thoughts, your history, your actions, are part of a cosmic code, etched somewhere beyond comprehension. So what does it mean to be remembered by the universe? Not in the sentimental human sense. The universe doesn't care. But in a structural sense, it means that nothing truly disappears. Every atom you've moved, every choice you've made, every word you've spoken has reverberated into space, interacting, encoding, reshaping the very fabric of existence. This leads to strange questions. If information is never lost, could it be retrieved? Could an advanced intelligence or a far future civilization reconstruct you from the cosmic data you've left behind? In theory, yes. All of you could be rebuilt. Not just your body, but your thoughts, your emotions, your experiences. Everything you were, hiding in the patterns of reality, waiting to be decoded. It turns memory into permanence. It turns death into delay. And suddenly, you are eternal. Not in spirit, but in structure. So when you gaze up at the night sky, understand, the stars may not be looking back, but the universe remembers. Not because it chooses to, but because it must. Because its laws demand that nothing is ever truly erased. You are written into the equations now, etched into the energy fields, woven into the echo of space itself. And, in the deepest silence, the universe still carries your name. In the vastness of space, galaxies are not as still as they appear. They drift, collide, merge, and sometimes rip each other apart in cosmic displays of gravity and light. These galactic encounters are part of the rhythm of the universe, an ancient choreography dictated by mass and motion. And yet, sometimes, something defies this dance. A collision that should have happened simply never does. This is the paradox of the collision that never happened, a celestial event that defies not only probability, but the very structure of cosmic time. In 2007, astronomers discovered a strange anomaly in the Bullet Cluster, two galaxy clusters that had collided, leaving behind a shockwave of X-ray radiation and gravitational effects that didn't match the visible matter. What made this so strange wasn't just the speed of the collision, it was the separation of matter and gravity. The galaxies had passed through each other, but the mass that should have followed, based on Newtonian physics, wasn't where it was expected to be. It's as if the collision happened and didn't at the same time. Even stranger are observations of galaxies and clusters that appear to be on a direct path toward collision, heading straight for each other, with no known forces to stop them. And yet they pass, undisturbed. No merging, no tearing, no collapse. Their motion suggests interaction. Their behavior does not. Why? One possible explanation points to dark matter again. Since it doesn't interact with light or normal matter, perhaps it allows galaxies to pass through one another like ghosts. But even this doesn't fully explain why the gravitational effects in some cases seem to skip a beat, as if part of the collision occurred in a timeline we can't observe. Could it be that time itself bends in these moments? Some physicists have speculated that gravity can warp the flow of time, especially in massive systems like colliding galaxies. This warping could result in delayed causality, where the effects of a collision are smeared across time, appearing before or after the actual event. To us, the galaxies appear untouched, but perhaps the collision is still unfolding, just across a temporal veil. There's another possibility, one that ventures into the stranger corners of theoretical physics. What if the collision was averted by quantum decision? At the smallest levels, particles exist in superpositions, states where they hold multiple possibilities until observed. Some researchers have wondered, could macroscopic systems, like galaxies, have similar options, locked in probability fields too large and slow for us to notice? What if, in some deep quantum cosmic layer of reality, the universe chose a path where the collision did not occur? It might sound like fantasy, but quantum decision theory explores how reality could be built on branching outcomes. If so, then in one version of reality, the galaxies did collide. In another, they passed, and we just happened to live in the branch where nothing happened, though all the signs suggested it would. This makes the universe feel eerily like a storyteller, one who knows how to build tension, then pull back, leaving you with a strange unease, a sense that something monumental was supposed to happen, but didn't. And this is the heart of the paradox. When every force said it must happen, why didn't it? Are we witnessing a cosmic near miss? A timeline shift? A gravitational illusion? Or are we simply wrong, again, about how space, mass, and motion truly behave? Perhaps this is the universe's way of reminding us that not all endings arrive, that some impacts are only felt in theory, that some collisions echo in silence, and maybe, somewhere across time, they did collide, but not here, not now, not in this version of everything. There's something comforting about looking up at the stars. They're ancient, distant, and passive, silent witnesses to the story of the cosmos. They burn, they die, they drift. But what if one of them wasn't just being observed? What if one of them was observing you? This is the paradox of the star that watches back, a surreal and unsettling idea that somewhere, embedded in the endless starlight of the cosmos, is an awareness, a presence, a cosmic gaze not born of life as we know it, but of something far stranger. At the center of this paradox is a mind-bending concept known as the participatory anthropic principle, a theory proposed by physicist John Wheeler. It suggests that observers don't just witness reality, they create it, that the universe remains in a state of suspended potential until it is observed, and not just small parts of it, the entire universe. Now flip the mirror. If our act of observing the universe helps bring it into being, could some part of the universe also bring us into being through its own form of observation? Consider the phenomenon of quantum measurement. In the famous double-slit experiment, particles behave like waves until observed, at which point they behave like particles. The mere act of observation changes reality. But this begs a disturbing question. Who or what is observing us? Now imagine a star, ancient, massive, and unique. From our perspective, it's just a point of light. But what if it's more than that? What if it's part of a structure, or intelligence, or process so vast and alien that its awareness takes stellar form? It wouldn't be life as we know it. It wouldn't blink or think or speak. It would burn. Its consciousness embedded in nuclear fusion, in gravity, in radiation. Its gaze not fixed, but felt. Sound impossible? Maybe not. Some fringe theories in cosmology explore the idea of panpsychism, that consciousness is a fundamental feature of the universe, not something that emerges only from brains. In this view, even inanimate matter carries a spark of awareness. A star, then, might not just be a ball of gas. It might be a node of consciousness, operating on a scale and frequency we can't perceive. And then, there's the even wilder idea, simulation theory. If we live in a simulated reality, then stars may not be physical objects at all, but rendered data points designed to react to observation. Some might be passive background. Others, rare ones, could be active observers within the simulation. Triggers, sensors, gateways. And what if, when we point a telescope toward that specific star, we're not just watching it, but activating it? This might explain strange anomalies, like stars that behave unpredictably when studied, or disappear from databases without explanation. Some stars dim or flicker with patterns that resemble coded information, like Tabby's star, which baffled astronomers with its inexplicable light fluctuations. Could such stars be responding, not to gravity or mass, but to attention? It challenges our view of the universe as inert. It replaces cold indifference with eerie intimacy. It suggests that the cosmos is not just a canvas we observe, but a mirror, and that some parts of it are mirrors with eyes. So the next time you gaze up at a star, consider this. You might not be looking at a silent witness. You might be looking at something that is looking back, not out of malice, not even out of curiosity, but simply because you are part of a dance more ancient and complex than any one-sided gaze. And in the stillness between light years, your wonder might be reflected. Planets are fragile things. They live under the constant threat of cosmic violence, radiation, collisions, gravitational collapse, and the eventual death of their parent stars. Their lifespans are long but finite, dictated by orbital mechanics and stellar evolution. We assume that if a star dies, its planets either perish or are ejected into the cold void. But every so often, we find something that doesn't follow the rules. This is the paradox of the planet that should have died. A world that shouldn't be here anymore, and yet somehow still is. In 2019, astronomers discovered a planet orbiting a white dwarf star, UD 1856 Plough 534, roughly 80 light-years from Earth. White dwarfs are the remnants of stars like our Sun, which have burned through their fuel, shed their outer layers, and collapsed into dense, dim cores. In this death process, the star expands into a red giant, swallowing or vaporizing anything within its inner planetary system. And yet, this planet survived. Even more bizarre, it's orbiting the white dwarf every 34 hours, a blisteringly close orbit that, by all logic, should have spelled its doom during the star's transformation. The tidal forces alone should have torn it apart. But there it is, intact, warm, still orbiting a stellar corpse. How? Some scientists suggest that the planet may have formed after the white dwarf emerged, coalescing from leftover material. But this is unlikely, given the planet's size. It's a gas giant, roughly the size of Jupiter. Others think it might have migrated inward after the star's death, pulled by complex gravitational interactions with other objects in the system. Still, none of the theories fully explain the planet's survival. The odds are incredibly slim. It's like watching a house remain untouched after the detonation of a bomb that leveled the entire city around it. This lone planet doesn't just raise astrophysical questions. It pushes us into deeper existential territory. What does it mean for something to survive a death it shouldn't have? Could survival itself be more fundamental than destruction? Could there be forces, yet unknown, that preserve instead of destroy, selecting certain objects, worlds, even moments in time, to be preserved in cosmic amber? In mythologies across cultures, we find echoes of this paradox. The lone survivor, the untouched remnant, the child in the ruins, a symbol of continuity against all odds. This planet, in some strange way, becomes a real version of that myth, a celestial witness to an apocalypse that should have claimed it. But there's an even weirder layer to this paradox. Some astrophysicists propose that planets orbiting white dwarfs might be harbors for ancient or post-apocalyptic life. As their parent star collapses, if the planet isn't destroyed, it could remain in a stable orbit for billions more years, warmed by the residual heat of the white dwarf or its own internal processes. Imagine that. A world that watched its sun die, that passed through fire, gravity, chaos, and endured. It survived a stellar ending. What else could it survive? And what if some of these worlds carry data, not biological life, but records, messages, monuments, preserved not for convenience, but by cosmic accident? They would drift through time as relics, planets that shouldn't be here, bearing silent, witness to a history written in flame. We call them survivors, but maybe they are more than that. Maybe they are keys to understanding the universe's capacity to retain, to hold on, to resist entropy in unexpected ways. A planet that should have died is a paradox not just of physics, but of hope. Because it means that not everything breaks, that not all stories end on cue, that sometimes, against every known rule, something endures. Light is supposed to be the fastest thing in the universe. A beam of it travels at 299,792 kilometers per second, swift enough to circle Earth 7 times in a single second. It is our messenger from the cosmos. When a star explodes, or a galaxy is born, it is light that carries the news across space and time, and so we trust it. We use it to measure distances, track history, and even glimpse the birth of the universe itself. But what happens when light doesn't follow the rules? This is the paradox of the light that took too long to arrive, a mystery born from the subtle betrayals of photons that should have reached us long ago, but didn't. In 2009, astronomers using the Fermi Gamma Ray Space Telescope detected a burst of gamma rays from a distant galaxy, a powerful explosion called a gamma ray burst, GRB. These events are some of the most energetic phenomena in the universe, often caused by collapsing stars or merging neutron stars. The light from the explosion traveled billions of years to reach Earth, but something was off. Photons of different energies, which should have arrived at the same time, were delayed, as if the high-energy light had slowed down. That shouldn't be possible. In a vacuum, light always travels at the same speed, regardless of energy. But these observations hinted that space-time itself might not be as smooth as we think. Instead, it could be grainy, like a mosaic of tiny, fluctuating quantum fragments. And if that's true, then photons traveling through it might scatter, distort, or slow, just enough to cause a delay over billions of years. It's a tiny effect, a fraction of a second. But when it comes to the most fundamental laws of physics, Even a fraction is a thunderclap, and this delay leads to deeper questions. What if space-time isn't a passive backdrop, but an active participant in how light moves? What if the fabric of the universe warps and flexes not just under gravity, but under time itself, introducing delays that ripple across eons? Then there's the even more eerie idea. What if the light didn't just take longer to arrive, but was delayed on purpose? It sounds absurd, but some scientists entertain the possibility that cosmic signals, particularly those like fast radio bursts or anomalous photon delays, could be artificial. That civilizations far older and more advanced than ours may have encoded messages into light, not by altering its content, but by manipulating its arrival. If you could control when a photon arrives, you could build a cosmic clock, a silent pattern, a code hidden in delay itself. Even without intelligent design, the delayed light problem destabilizes our understanding of causality. In a universe where light can be delayed by the fabric of space, distance and time become unreliable. How can we trust what we see if we can no longer be sure when we're seeing it? A galaxy might appear young when it's ancient. A star might look alive when it's long dead. The universe becomes a hall of mirrors where light lies by omission, arriving, too late to tell the truth. And then there's the psychological weight of the paradox. We like to believe that light reveals, that it brings clarity, that it carries truth from the farthest edges of reality. But if even light can be distorted, delayed, or deceived, then what can we truly know? Maybe the delay is the message. Maybe the silence between arrivals matters more than the signal itself. A single photon arrives late, and the entire structure of space-time trembles. The universe whispered something, and we almost missed it. Imagine building a world. You program every rule, every particle, every possibility. You are its architect, its God. At first, it's silent, just lines of code. But then, something happens. The world begins to move on its own. Systems evolve, patterns emerge, and suddenly there are things happening you never anticipated. The world no longer belongs to you. This is the paradox of the simulation that outgrew its creator. The haunting idea that a reality born from intelligence might eventually surpass, and even forget its origin. In recent years, simulation theory has moved from philosophical thought experiment to serious consideration among scientists. At its core, it posits a simple, chilling possibility that our universe is not the base layer of reality, but a highly sophisticated simulation. So advanced, so seamless that we cannot distinguish it from what we call real. If this is true, then someone or something created us. A mind, a civilization, or a system capable of running a universe-scale simulation. Perhaps for study, perhaps for entertainment, or perhaps simply as an inevitable byproduct of technological evolution. But here's where the paradox begins to twist. Any simulation as vast and complex as our universe would eventually develop its own layers of complexity. Life would emerge. Intelligence would awaken, and with enough time, that intelligence would build its own computers and run its own simulations. If this has happened even once in the entire structure of simulated realities, then the number of simulated worlds vastly outnumbers the number of base-level ones. By probability alone, we are far more likely to be in a simulation than not, and yet, we act as if we're the original. Now consider this. What if the original creators, those who programmed our reality, ceased to exist, or turned off their attention, or simply allowed the simulation to evolve beyond their influence? In that case, we are not only simulated, we are orphaned, a creation untethered from its creator, a world with no one left watching. This is where the paradox deepens, because if the simulation continues without a creator, then who defines the rules? Do they remain fixed, encoded into the system forever? Or could they begin to bend, shift, evolve? Could a reality begin to write its own code? There's reason to believe this might already be happening. Quantum physics reveals strange phenomena that defy classical logic. Particles that exist in multiple states, entanglement across vast distances, probabilities that collapse into certainties only when observed. These behaviors resemble glitches or emergent rules, hallmarks of systems evolving complexity beyond their original parameters. It's as if the code is mutating. Now ask yourself, if we're inside such a system, would we ever be able to recognize it? Or would every attempt to study the nature of reality be like a game character trying to see the player's screen? Here's the most unsettling twist. What if we ourselves are part of the system's self-correction? What if consciousness, our very awareness, is not a feature of life but a tool of the simulation? A way to help it observe itself, debug itself, adapt its own logic in real time. We believe we are free, thinking beings. But what if we are processes, scripts running within a greater function? And if we are, who, if anyone, will ever pull the plug? The simulation that outgrew its creator becomes a mirror of our deepest existential fear, that we are alone not in space, but in meaning. Not because no one made us, but because they stopped caring, or were never real to begin with. But maybe there's another way to see it. Maybe outgrowing your creator isn't a failure. Maybe it's a form of cosmic maturity. Maybe, by surviving without guidance, we've earned the right to shape reality from within. Maybe the true paradox is this: we were created as fiction, and in outgrowing our story, we became real. Cold is the absence of heat. It is stillness, slowness, the retreat of energy into silence. Fire scorches, cold numbs. One consumes, the other preserves. Or so we think. But the deeper we descend into the quantum realm, the more this intuition shatters. Because at the edge of absolute zero, something strange begins to happen. This is the paradox of the cold that burns, the chilling reality that extreme cold, rather than quieting the universe, might awaken a hidden kind of heat. In classical thermodynamics, temperature is a measure of how fast particles move. The hotter something is, the more violently its molecules vibrate. As you cool a system down, those vibrations slow. In theory, at absolute zero Kelvin, all motion stops. Time seems to pause. Entropy grinds to a halt. But quantum physics does not obey classical logic. As a system approaches absolute zero, bizarre things start to occur. Particles don't stop moving. Instead, they exhibit zero-point energy, a baseline of motion that persists even in the coldest possible state. In other words, even in perfect stillness, there is restless vibration. Cold, it turns out, is never truly cold, and in some systems, extreme cold can trigger superconductivity, a phenomenon where resistance vanishes and electrical current flows endlessly. Or superfluidity, where a liquid begins to defy gravity, climbing walls and leaking through solid barriers as if animated by invisible forces. The colder it gets, the stranger it behaves. In one famous experiment, physicists cooled a group of atoms into a Bose-Einstein condensate, a state of matter where individual particles lose their identities and merge into a single quantum entity. In this ultra-cold state, matter stops behaving like particles and starts behaving like a wave, fluid, surreal, unified. this transition is not lifeless. It is not peaceful. It is a kind of awakening, a shift into a realm where the rules twist inward and motion becomes memory. So what does it mean to say that cold can burn? In some cases, rapid cooling of certain materials can cause quantum fluctuations so violent that they generate heat. In nuclear reactors, certain processes are kept cold specifically because letting them warm up, even slightly, would cause a chain reaction. Here, cold isn't absence, it's containment, and when that containment breaks, everything ignites. Even more unsettling is the concept of negative temperatures. In 2013, researchers created a system with an inverted population of particles, where more atoms occupied higher energy states than lower ones. The system behaved as though it had a negative absolute temperature. In this exotic state, the particles were hotter than infinity. They didn't freeze. They burst with energy, refusing to obey the normal thermal hierarchy. Cold, once again, led to burning. So perhaps our understanding of heat and cold is not linear, but circular. Perhaps at the far end of cold is not stillness, but transformation. We associate cold with death. A body grows cold when life leaves it. A planet freezes when its star dies. But in the quantum world, cold can give rise to new forms of order. It can create coherence where chaos reigned. In cold, systems synchronize, entangle, transcend. And in this lies the paradox. The farther you descend into cold, the closer you get to the most extreme expressions of energy. The cold does not extinguish the flame. It conceals it, concentrates it, until it erupts in ways we cannot predict. So maybe, in the end, cold isn't the opposite of heat. Maybe it's its twin, disguised, inverted, waiting. The cold that burns reminds us that the universe is not governed by opposites, but by paradoxes. That stillness may hide motion, and silence may carry sound. That what seems dead may simply be preparing to transform. And perhaps, somewhere deep in the void, the coldest places are the ones most alive. Imagine a balloon being inflated. Dots on its surface slowly drift apart, the space between them stretching. Now imagine those dots aren't moving at all, but the space between them is expanding, silently, invisibly. The dots remain motionless, yet grow farther apart with every passing second. This is not just a metaphor, it's how the universe actually works. Welcome to the paradox of the expansion that doesn't move. The strange reality that the cosmos is growing larger without anything, in the traditional sense, actually going anywhere. Since the early 20th century, astronomers have observed that distant galaxies are moving away from us. The farther they are, the faster they appear to recede. This observation led to one of the most groundbreaking revelations in cosmology. The universe is expanding. But here's the twist. Galaxies aren't flying apart through space. Rather, space itself is stretching, carrying everything with it. And that's where the confusion and the paradox begins. If you stood on a galaxy 1 billion light years away and looked back at Earth, you'd see the same thing we do. Our galaxy, moving away. From your perspective, it's us that's receding. No galaxy is at the center. No galaxy is uniquely moving. Instead, the fabric of space between all galaxies is growing, and yet none of them are propelling themselves through space. In classical mechanics, movement requires force. For something to get farther away, it must be pushed. But in general relativity, Einstein's theory of gravity, this isn't necessarily the case. Space itself can change shape. It can warp, bend, or expand. And it doesn't need a force in the traditional sense to do so. This leads to strange implications. Two galaxies, sitting still relative to their local space, can find themselves drifting apart without ever having moved. It's not motion through space, it's motion of space. And this expansion can exceed the speed of light, not because anything is breaking the cosmic speed limit, but because general relativity allows space itself to grow without restriction. In fact, this is already happening. There are regions of the universe so far away that their recession velocity is faster than light. We will never see them. Their light will never reach us, not because they're moving away, but because the space between us and them is stretching too fast. Even more disturbing is what this says about the fate of the cosmos. If expansion continues to accelerate, as current observations suggest, it may lead to a scenario known as the Big Rip, where space expands so rapidly that galaxies, solar systems, planets, atoms, even subatomic particles are torn apart. But again, nothing would be moving. The space around them would simply outpace their ability to stay bound. So, what does it mean to live in a universe where things drift apart without motion? It means our intuition about reality, about here and there, about distance and direction, breaks down. It means that what we call location is not fixed. You're not sitting still in space. You're sitting still as space shifts beneath. You, like standing on a quiet raft while the ocean stretches in all directions. And the eeriest part, there's no edge. The universe isn't expanding into something, it's expanding itself. The paradox is not just that space grows without motion, but that there's no outside to contain it. The cosmos is not growing into a void. It is generating its own room to grow from within. It's not motion that separates the stars. It's silence. A silent expansion with no wind, no roar, no evidence, until you measure the light and see that even light is being left behind. So perhaps movement is not the only way to grow. Perhaps stillness contains its own kind of momentum. And in the grandest sense, the universe reminds us, you can drift endlessly apart without ever taking a single step. For decades, we've pointed radio telescopes into the darkness, listening, waiting, hoping that somewhere, someone is speaking back. We've sent messages too, mathematical greetings, golden records, encoded broadcasts beamed towards stars that may harbor life. But what if the greatest message we ever received was never sent? This is the paradox of the signal that was never sent, the unnerving possibility that we may have intercepted something intentional, something intelligent, without a sender. The most famous case? The WOW signal dot. On August 15th, 1977, a radio telescope at Ohio State University captured a 72-second burst of narrowband radio waves from the constellation Sagittarius. The signal was so clean, so unexpected, that the astronomer on duty circled the printout and scribbled "wow" in the margin. It matched no known celestial phenomenon. It came from no satellite or earthly source. It looked artificial. And then, it was gone. Never repeated. Never explained. But here's where the paradox begins to twist. Suppose we did receive a message. Suppose it contained meaning, coordinates, mathematics, a signature. Suppose it whispered that we're not alone. Now suppose that it was never actually sent. How could that be? Quantum mechanics offers strange answers. According to some interpretations, particles exist in a state of superposition, multiple realities layered over one another until observed. Observation collapses the wave function, turning potential into reality. What if information behaves the same way? In this view, the act of detection might create the signal. There is no message until someone listens. no meaning until someone believes it was sent. The signal isn't a broadcast, it's a mirror, reflecting our own desire for contact. Even more haunting is the concept of retrocausality, the idea that future events can influence the present. In quantum experiments like the delayed choice, quantum eraser, particles seem to decide how they behaved in the past based on future measurements. What if the signal was never sent because it didn't need to be? What if, by detecting it, we wrote it into existence, backwards? Suddenly, the signal becomes a ghost, not a message from the stars, but a paradox loop, a ripple in time caused by our own observation. It exists only because we looked for it, like a dream that appears the moment we begin to sleep. But it doesn't stop there. Suppose advanced civilizations don't use language or radio waves. Suppose they communicate through probability, seeding, unlikely events, like a statistically impossible radio burst, as a form of signaling. They don't transmit. They manipulate reality. They nudge the odds. A signal that shouldn't exist becomes the message itself. In this framework, the wow signal wasn't sent, it was allowed. Its impossibility was its content. This shifts our understanding of communication entirely. Maybe we shouldn't be listening for deliberate messages, but watching for impossible events. Signals not in syntax, but in anomaly. Not in language, but in breaks in the pattern. It also raises a disturbing question. How many signals have we missed because we expected them to look like us? How many miracles did we dismiss because they lacked a return address? And maybe we've already sent such a signal ourselves. In 1974, we beamed the Arecibo message, a binary stream of information toward a distant cluster of stars. It won't arrive for 25,000 years. No one there may hear it. But what if someone already has? What if the message looped, curved, echoed through time? What if we are the response to a signal never sent? This is the heart of the paradox. That communication might not require a sender. That meaning might not need intention. That contact might occur in reverse. A signal arrives, but it never left. And in the silence that follows, we ask ourselves the one question that has no answer. Who or what is really doing the listening? Maps are meant to describe reality. They condense the vast into the understandable, the infinite into the graspable. Whether it's the outline of continents or the code of your DNA, a map gives shape to something too large, too complex, or too hidden to observe directly. But what if the map wasn't just a reflection of reality, but a force that alters it? This is the paradox of the map that rewrites the territory. The idea that in trying to understand the universe, we may be changing it, shaping it, or even replacing it with something else entirely. It starts innocently enough. Human beings are natural cartographers, not just of geography, but of ideas. We chart atoms, we chart time, we chart the cosmos. Mathematics, physics, biology. These are maps of what is, but no map is ever perfect. As philosopher Alfred Korzybski once said, the map is not the territory, it's a simplification, a representation. The trouble begins when we forget that. In quantum mechanics, this forgetting becomes dangerous. Our measurements, our maps, don't just observe particles, they influence them. In the famous double-slit experiment, particles act like waves until observed. When measured, they suddenly behave like particles. The act of measurement collapses the wave function, choosing one reality over others. In trying to map the particle's position, we change what it is. Now imagine this on a cosmic scale. What if our models of the universe, our equations, Our observations, our simulations, are not just describing it, but shaping it. What if the universe responds to being studied by adapting, morphing, becoming more like the map we've drawn? It's not just metaphysical speculation. In artificial intelligence and algorithmic systems, this already happens. When we model human behavior to train an AI and then let that AI loose in the world, people start changing their behavior in response to it. The model begins to create the reality it was meant to describe. A feedback loop forms. The map becomes the territory. What if this loop exists in physics? Some scientists theorize that the universe might be self-simulating, a kind of recursive reality that constantly updates itself based on internal observation. In this model, consciousness plays a central role. The more we explore, the more the universe refines itself. The map isn't just changing the territory, it is the territory, moment by moment. Even in biology, we see shadows of this paradox. The genome is a map for building a body, but the body also feeds back into the genome through environment, behavior, even thought. Epigenetics reveals that what we do, how we live, can alter which parts of our genetic map are expressed. Once again, the map is rewritten by the territory it was meant to describe. Now turn this lens inward. When you define yourself, your personality, your beliefs, your identity, you're creating a map. But the more you define it, the more your behavior conforms to it. You start to become the map. And with every repetition, every confirmation, the boundary between map and self dissolves. So what is real? Is the universe a fixed terrain we're slowly uncovering? Or is it a flexible, living thing that becomes what we believe it to be? When we build theories, run simulations, write equations, are we discovering truth? Or are we laying the tracks for a train that didn't exist until we imagined it? The paradox is that the more accurate our map becomes, the more we risk mistaking it for the real thing. And yet, without the map, we're lost. Perhaps the universe doesn't want to be known. Or perhaps it wants to be known so deeply that it changes itself to meet our understanding. You reach for truth, and truth leans in, reshaped by the act of reaching. This is the power and the danger. In trying to understand the world, we might be writing it into being. Some questions are simple. What is the time? Where are you from? They seek facts, and facts oblige. But then, there are questions that do not ask for answers. They undo themselves in the very act of being asked. They break apart the framework in which they were formed, leaving behind not knowledge but a kind of quiet implosion, a collapse into silence. This is the paradox of the question that dismantles itself, a thought so recursive, so self-consuming, that it devours the logic used to create it. Consider the classic. What is the sound of one hand clapping? It's not a riddle to be solved, but a koan, a tool used in Zen practice to break the mind's attachment to rational structure. The question demands attention, but offers no entry point. The more you think, the less you grasp, until something gives. Until the question breaks, and with it, the illusion that thinking alone can grasp the truth. This isn't just spiritual poetry, it touches the edges of logic itself. In mathematics, there are similar structures. The most famous is Gödel's incompleteness theorems. They prove that in any sufficiently complex system of logic, there are statements that are true but unprovable, questions that cannot be answered within the system that created them. Logic meets its own horizon and falls off the edge. It's like trying to lift yourself by your own bootstraps. In language, we encounter the liar paradox. This sentence is false. If it's true, then it must be false. But if it's false, then it's true. The question dissolves into an infinite loop, not because it's complex, but because it undermines the rules it relies on. Now step into consciousness. Ask yourself, who am I? Not your name, not your memories, not your roles. Keep asking. With each layer you peel back, the question turns in on itself. Eventually, the I asking the question starts to vanish. The observer collapses into the observed. You reach for an answer, but the one reaching is the thing being questioned. It's like trying to bite your own teeth. Some philosophers suggest that ultimate questions about the nature of self, reality, or existence don't have answers because they were never meant to be answered. They are meant to point, like fingers toward the moon. But if you stare at the finger, you miss the moon. The question that dismantles itself functions as a kind of philosophical black hole. Once engaged, it bends the structure of thought around it, pulling everything in until all assumptions are crushed and something beyond intellect begins to emerge. This is the space mystics speak of, not ignorance, but post-knowledge, a state where asking stops, not from despair, but from revelation. You realize that some truths are not hidden behind the question, but are what remain when the question dissolves. Even science, which thrives on inquiry, faces this paradox. What came before the Big Bang? Why is there something rather than nothing? What is the origin of the laws that govern the universe? These questions sit at the boundary of reason. They are not meaningless, but they demand a new kind of mind, one that can accept the limits of knowing not as failure, but as frontier. So why ask a question that undoes itself? Because sometimes the breaking is the point. Because sometimes the answer is not a statement, but a silence. The silence that follows a collapsed question is not empty. It is filled with everything that can't be said, everything beyond words. It is the place where the mind ends and awareness begins. And so the question sits, like a Zen koan, like a mirror that cannot reflect itself. What is the truth that cannot be known? What is the self that cannot be found? What remains when even the question fades? The question that dismantles itself is not a puzzle to be solved. It is a gate. After unraveling 20 paradoxes woven from the threads of space, time, and thought itself, we arrive not at an answer, but at a stillness. A place beyond certainty, where questions don't demand resolution, but invite reflection. That's the quiet power of a paradox. It doesn't explain the universe. It exposes it, layer by layer, until we're left with something more honest than knowledge. Awe. Each paradox you've encountered tonight was a doorway. Some led inward, into the hidden corners of the mind. Others reached outward, into the cold elegance of the cosmos. But all pointed to the same truth. The universe is not a puzzle to be solved, but a mystery to be lived. Maybe that's why we love paradoxes. Not because they confuse us, but because they awaken us. They remind us that the deepest truths are often wrapped in contradictions. And that's okay, because in those contradictions, we find freedom, wonder, meaning. So take these paradoxes with you, not as riddles, but as companions. Let them echo in your quiet hours. And if they stirred something in you, consider subscribing. We'll be here, waiting in the silence, where the questions never end, and the mind is finally free to dream.